and repeat. Newton's method is iterative method. It's means that it's a guess check method. So we start off with an initial guess, plug it into a formula. That formula gives us the next logical approximation where we start. And then we repeat the process until we get to the goal, which is to find where the function crosses the x-axis. Currently, we know formulas solve simple equations like linear equations. Linear equations. Quadratic equations. We know the quadratic formula. We know the difference of two squares. We know the sum and difference of two cubes. But if they're in a particular pattern, we have formulas to fix them. But there are more equations that don't have formulas that solve them. This is where Newton's method comes in. Basically, this is what it looks. Oh, well. The value x that makes f of x equals 0 is called the root of the function. The solution is the f of x equals 0. So the root and solution are pretty synonymous. The x is the root. Plug in the root inside the function, you get the 0. You get the solution. Another name for these things is called the x-intercept. So the root, x-intercept, the solution, the factor, all these are synonymous, really. They mean the same numbers. Let's see how this thing works. The equation that we're going to use pretty much for this process, well, let's see what this means. Let's say we had a quadratic equation. There's root number 1 and root number 2. This is how we do it. So these are the x values that are x-intercepts. So we pick a value somewhere that's not those. Let's say this is 4 and this is 1. Let's say I pick 5. I get a point on that curve. The tangent line to that curve at that point where it crosses the x-axis is now my next. This was my first guess. This was my initial guess. Once I find that, I find the tangent line at that point, and where it crosses, that's my next guess. That's what I repeat the process. And then I find a closer one, and a closer one. Eventually, it gets so close that I get to the actual x-intercept. This is how Newton's method works. You start off with a guess, plug it into the equation, find the tangent line, the equation of the tangent line, find out where it crosses the x-axis, and that point is your next guess. You start at that point. That's your next one. That's why it's iterative. It repeats itself. So to find the value of y, we start off with the function x sub n, because we don't know how many guesses we're going to have. And then we look from there because we need to have the slope of the tangent line, which is the first derivative. And we have to have our delta x. What does delta x represent? The distance between one point to another point. So our equation that we're going to look at is x minus x sub n, where x is our solution point. All right, so let's look how this thing derives. The point where it crosses the x-axis we can find by setting the initial y to 0, if it's doable. So what we have here from our equation if we set y equal to 0, what do we have? Oop, these are m's. Let's solve for this, because we want to see how far we are from the answer, because we're eventually trying to get to the value of x. How do we solve for x? Subtract f of x sub n remember, we're trying to solve for x. So next we do get rid of the first derivative. And slowly you'll see also what we've been dealing with in some of our equations in the last couple of weeks. And then we add x sub n. So the x values so this is the formula we'll use to approximate the next value for x. Now, since what does x sub n represent? Well, remember the initial guess is x sub 0. That will lead us to our next guess. So that becomes our next guess, which leads us to our next one. That'll be our input. Our output is the next one. It's a counter. So since these are all x sub n, this one is n plus 1. It's the next x we're going to use. We can do this as long as the denominator is not equal to 0. When would the denominator equal 0? the denominator equals 0, when we have a vertex. Why will vertices not help us? A vertex, remember, it's the highest or lowest point. What do we need from our equation? And why does that have to be non-zero? We have to have what does the derivative represent? The slope of the line tangent. It's that slope of the line tangent that finds us our next x-intercept. So once we find this one, we plug it in there. That gives us that value. We get that slope. That gives us this point. We plot this one. You see how each point gets us closer and closer, closer to the x-intercept. That's how this is going to work. So you can't do it by hand. You'll have to use a computer or a computer that does repetitive work because it's just algorithmically based. The formula is let's look at the first example then. The first example says approximate the positive root of this equation. What do we know about that equation? It's what? It's quadratic. Okay, what else do we know about it? It opens up because the leading coefficient is positive. It goes down 2, right? So because it opens up and it went down 2, we know we're going to have 2 solutions. So what we have to do here are the steps. Make an initial guess for x sub 0. Remember, we're trying to solve this equation. The formula we'll be using so let's look at this. What do we need so we can use this equation? We have the function f of x. Do we have the derivative? No. We got to find the derivative, which is what? 2x. So our equation that we'll be using looks like this. Our initial equation goes on top and 2x goes on the bottom. Now, these are indices. You could leave it like this if you want to, or you can split them up. Because we have an x sub n here, and these are x sub n's already. You could combine them there if you want. So I can have x sub n squared over 2x sub n minus minus makes it a plus 2 over 2 x sub n. So here I have x sub n. One of these x sub n's cancel. So I have an x sub n over 2. The 2's cancel. So I have 1 over x sub n. So we have 1 x sub n minus a half at x sub n makes it x sub n over 2. So this will make an easier equation. We can just plug them in there. Since both of these are x sub n, we have 1 over 1. We can make it 2 over 2. 2 minus 1 is 1 over 2. Okay, now we begin. Did I give you all in your sheet? Did I give you all the table? No. No. Oh, wait. So we'll be using this equation. Let's use this table. These are my x sub n's. This is n plus 1. This is x sub n. So our first x, what's our first initial guess? Let's just try one. Try something simple. So if we plug in 1 in place of here for x sub n, we get 1 over 2 plus 1 over 1, 1/2 plus 2 over 2 is 3/2. What is our function at x sub n? Because what are we looking for? What value do we want from x sub n? F of x sub n. We're looking for what? We're looking at the x-intercept. We're trying to find the x value that'll give us an x-intercept. So when we first put in x sub 1 inside there, we get 1 squared minus 2 is -1. So this is our f of x sub n. That's at 1. Our y value at -1. So let's try at 3/2. So we get 3/2 squared minus 2. 9 over 4 over 8 over 4 equals 1/4. Because this is 2 over 1, we need a common denominator. So I'm multiply 4 over 4. So we're getting closer. So here we start off at 3/2. Plug them into this equation. We have 3 over 2 divided by 2 plus 1 over 3 over 2. What happens to this first compound fraction? How do you solve that one? Yeah, keep the top alone and flip the bottom. Keep the top alone and flip the bottom. So we have 3/4 plus 2/3. Get a common denominator, which is going to be 12. So we have 9 plus 8, which is 17/12. So now we plug this in there, 17/12. And we keep on going. So you see now why using a calculator this should be very painful, because this would give us 17 squared over 144 minus 288 over 144. We've got to square the first, this is x squared minus 2. Yes.
Don't just set it to 0 and solve for everything? Because wouldn't the
Okay, okay, whenever you learn a new method, always start off with something that's easily doable, that you can always check it, because you won't always have easy ones to work with. So you have to learn how to use the method first, and you use it by using simple numbers first.
set it to 0 and solve for it?
Right. Because if you can solve it another method, do it. If there's a formula for it, do it. But this method is used for equations, which there are a lot more equations that can't be solved by what we know already. So we have to use these iterative process, which is why they were invented. Because there are a lot more of those that aren't solvable. So yeah, it's just, yeah, if we wanted to, we could set this equal to 0. We get x squared equals 2. And the answers, the x-intercepts are going to be at plus or minus square root of 2. And that's what's going to tell us these values here are going to approach plus minus 2. Well, no, because this is looking for the x-intercepts, either one. No, you can't do that. Yes, I see what you're saying. Because that's, well, in this case, since it's quadratic, yes, you can. But no, you can't, because what if there's a horizontal shift? If it was a horizontal shift, then you can't make that assumption that's just going to be a change of sign, because it could be both positives or both negatives.
So for this one, like, you, let's start at a point, like, we have to start farther, like in a negative point, so that we can find that negative intercept before being a positive, because like right now, we're only gonna get that positive intercept.
I'm glad you asked. Do we know any method to help us? Because it's the first guess that's the most important. Because you're right. By seeing the equation, we know it's quadratic. We know there's 2 solutions. And so we'll just try to isolate one first and then repeat the process, try to find the other one. But do we know a method to help us isolate where an x-intercept could lie? No. I see why you say that, but no. Let me give you a hint here. No, dude. Very good. What does the intermediate value theorem tell us? No, this and the squeeze method helped us solve that. The limit of sine x over x is 1. Intermediate value theorem says this. If I have 2 points, A and B, this is B. And f of A is one sine and f of B is another sine, then there has to be a point C in between there where it equals 0. So if my f of A, let's say, was 3 and f of B was -2, because these are on opposite sides of the x-axis and it's a continuous function, then there has to be a C value somewhere between there, at least 1 where it equals 0. So yes, what we could have done, we could have just used the intermediate value theorem and start finding values where it gives us opposite signs. So remember, we had our f of x equals x squared minus 2. Let's try at 0 and at 2. If x is 0, we get 0 squared minus 2, which is -2. If x is 2, we get 2 squared minus 2, which is 4 minus 2, which is +2. Okay, we know that between 0 and 2, it's got to cross the x-axis. So let's narrow it down even further. Let's try fx1. We have 1 squared minus 2. So now we know between 1 and 2. Between 1 and 2, since they're opposite signs, there has to be a value between there. Yes, we can keep on doing this method forever and ever and ever until we get down to 0. But there are, how many numbers are there between 1 and 2? Infinite. All the decimals to nth number of decimal points. So that's the reason we use Newton's method to find a better location. You notice how our last x we looked at was 3/2. 3/2 is 1.5. 1.5 is between these two guys. So we're getting closer and closer and closer. So we repeat the process until we get f of x equals 0. Or the way would computers do it is we let it run iteratively until we see the numbers get so eventually what you'll see something is something like f of x equals -1.24 e to the 47th. Oops. Or e to the -47th. It's even smaller. So what this means is this is the exponential. So we have 1.24 times 10 to the -47, which means the decimal place moves 47 places that way, 46 zeros, which means that's very, very close to 0. So close that we'll take it, we'll buy that. So that's why you use computers. And then the limit there is how accurate your values are going to be. It's called the degrees of freedom. How many degrees, how many decimal places till you're satisfied? All right, so yeah, we'll keep on going in this method until we get x equals 1.324717957. This is the table I should have put into yours, something like this. This is for the example x cubed minus x minus 1. These are your iterations. The first iteration is x of 0. You pick a value for 1 for your first x. Plug it in there. Plug it into your function, the derivative of the function, and then find your next value. That's your next value. Plug that x inside these and plug that into the equation. You get this. Now this is your next input. You keep on working out. And you see how it works. It gets to be so that once it starts repeating, then we know that that's our significant digit. You see why this was my field of studies in my master's program, numerical analysis, is where we took computers and wrote programs to do this for us. Again, Newton's method is the first one. Then we go to Euler's method. Then we go to Taylor's series and geometric and arithmetic sequences. But that's what's happening here. And each step, this x value, which is the x sub n plus 1, is now your next input, but it's getting closer and closer and closer to make your final answer 0. You notice this, you notice the answer here is this is the f value. You see how small it's getting? 0.002, 0.000009, negative 1.8 times 10 to the negative 13. So it'll have decimal 12 zeros, 1/8. So this is close enough to 0. And that's the whole process. Sometimes these things go on for thousands of iterations until you get to a good number. In Calculus 2, we're going to learn things called divergent convergent sequences and series, which we may talk about in this class, but we'll jump into it deeper next week. Let's look at the next example. Do we have another one? Yeah, we do. Actually, the next example was one I just showed you. Example 2. F of x equals x cubed minus x. Where it crosses the horizontal line, y equals 1. So find the x coordinate of the point where it crosses this function at the line y equals 1. Let's go ahead and draw the graph of this one first. How do we draw the graph of this one? Well, first off, we'd factor it if we can. So we have x, which makes it x squared minus 1. We can factor this out. It's the difference of two squares. So it's x plus 1, x minus 1. Let's see, set it equal to 0. Let's find the x-intercepts. So our first one is at 0. The next one is at negative 1. And the last one is at positive 1. It's an increasing function. And since the multiplicities are all 1, it crosses at those intercepts. Review of algebra. So that's that function. We want to know the x value where it crosses the horizontal line y equals 1. We want to know that x value. Which is where we get the function x cubed minus x minus 1. So now we'll repeat the process. We set up the equation and repeat the process. Remember, we have x sub n plus 1, x sub n, f of x sub n, f prime of x sub n, and then x sub n plus 1 equals x sub n plus f over f prime. Let me get to that table. Oh, it's minus, I'm sorry, because we're getting smaller. Okay, the question you should have is, why is it minus 1? You didn't ask. Because what we're looking for is, where is this equation equal to the line y equals 1? Here's the y of the function, and here's the y of the horizontal line. If we set it equal to 0, then we get that equation. Make sense now? Do not hesitate. If you have a question, ask a question. But I was looking at your eyes and you're wondering, where did you get that equation from? But you have the function, it says where it crosses the y-axis, the y equals 1. So those are all the important factors. That's that. And this is where you begin. You pick an initial x value. Because I'll make this n. My initial guess, I'm saying 1. This is x sub 0. So my f of x sub 0 is f of 1. And I plug it in there. 1 minus 1 minus 1 is negative 1. Because 1 minus 1 is 0, minus 1 is minus 1. And the derivative of this thing, so this is f of x, so we have to know the derivative, which is 3x squared minus 1. So the derivative at x sub 0 is 1. So we have 3 minus 1 is 2. We plug it in there. Because n is simply my counter. This is my initial guess. So that's my x sub 0. I start plugging those inside the function. So now I'm finding the next x value, which is x sub n was 1 minus negative 1 over 2, which is 1 plus 1 over 2 makes it 3 over 2, or 1.5. So since my counter increases to 1, my next starting bid is at 1.5. So this number comes all the way over here and starts the next round. So now I plug that value into both the F and F prime. One point five cubed, I'm not gonna do that. That's painful. But yeah, calculators and computers. It's easier if you use Excel. Because with Excel, I can create this is my X n plus one. This is my this is my n. This is my X sub n. This is my F of X sub n. This is my F prime of X sub n. And this is X n plus one, which is equal to X sub n minus F of X sub n divided by F prime of X sub n. So let me put the equation here. This is X cubed minus X minus one. Yeah, I gotta do it down here. This is this value cubed minus this value minus one. What? It's that value. So it's going to be E4 cubed minus E4 minus one. X cubed minus X minus one. There. And this one is 3x squared. So it's 3 times x squared minus one. This one's going to be that number minus that divided by that. This one's going to be that plus one. That really doesn't do anything for us. There. There. So what column is the most important column for us to look at? This one? Oh, this one. No. Because what are we trying to do here? We're trying to find the x value where it crosses the function crosses the x-axis, right? So what's the value of f when it crosses the x-axis? So we look at this function. When it goes down to 0, this is, but again, you see, this is because we only have 2 decimal places. If we want to be more accurate, we'd increase it to 15, 20, 40 decimal places. But this is the process. It's a lot easier using Excel than it is using calculators. Because you have to write a whole bunch of stuff down when you're doing calculators. This one, once you get the formula down, it gets much easier. Because notice how this begins there. This one comes from that. This one, so it just carries over. That's why this is x sub n. This is x minus 1 or plus 1. This is my next one. That's my next one. That's my next one. But see, we notice here that it changes. It stops there. So when x is 1.32 approximately, our y values are 0. So that's our x-intercept. One of them. Because remember, we have how many in this case? 3. We can repeat the process now of finding 2 other points. All right, so that's Newton's method. It's used a lot in engineering and physics. Because you don't know what the function is, you just give them the data. So that's that.